Welcome to the Chapter 8 of the Oil and Gas Engineering audiobook. In this chapter, we describe the work and the deliverables of the Materials and Corrosion discipline. This discipline is in charge of selecting the material of construction of all equipment and lines.
A large variety of materials of construction are used in oil and gas facilities. It includes ordinary carbon steel, as well as special types of carbon steel, such as low temperature carbon steel. Also, carbon steel can be used as galvanized carbon steel or other type of internal coatings, such as cement or rubber lined. It includes as well what is called corrosion resistance alloys, which are stainless steels. And again, there are various types of stainless steels. It also includes plastic pipes, such as glass reinforced epoxy, shown here, or special alloys, such as copper nickel alloys, shown here. The selection of the material of construction depends on the type of fluid handled, its corrosiveness, on its pressure, and its temperature. First of all, let's have a look at the pressure. The pressure of the carried fluid will induce the strength of the material of construction. Naturally, for high pressure, high strength material will be selected to reduce the wall thickness. In fact, the wall thickness is proportional or inversely proportional to the maximum allowable stress of the material, which is its strength. Therefore, a carbon steel twice as strong as an ordinary carbon steel would, for instance, be selected for a high pressure pipeline to halve its thickness. The second parameter that comes into play when selecting material of construction is the fluid temperature. Both high and low temperatures to which the material could be subject have to be taken into account. For instance, carbon steel is suitable for temperature range between minus 29 degrees Celsius to 427 degrees Celsius only. Below that, low temperature carbon steel, and then alloys up to stainless steel need to be used. Above that, stainless steels also have to be used. This shows, for instance, the material selection as per the usual piping code, showing that, for instance, stainless steel will go up to minus 254. And if one needs to go, for example, at temperature of 800 degrees Celsius, one has to also use stainless steel. The last parameter that influences the material selection is the type of fluid and its corrosion aspects. The last aspect that impacts the choice of the material of construction is the nature of the fluid and the type of corrosion it creates. Let's take an example, which is the most common corrosion phenomenon found in upstream oil and gas facilities. The fluids handled contain gas mixed with oil and water. Water gets acid because of the presence of acid gas such as CO2 and H2S in the gas. Acid water corrodes the steel. This phenomenon is described by a corrosion rate formula. Such formula gives the corrosion rate in millimeters per year, function of the temperature and the content of CO2, the partial pressure of CO2, which is the concentration of CO2 times the pressure in the line. Such formulas come from various publications, in particular research publications, and many are synthesized in API 581. As you can see, the corrosion rate is different for every difference of temperature and every difference of concentration of CO2. Therefore, this calculation has to be done for every line of the plant. The required input data for this calculation are shown on the heat and mass balance. Indeed, the heat and mass balance indicates for each of the stream the temperature, the pressure, as well as the composition. Therefore, the calculation of the corrosion rate can be done. This corrosion rate is then calculated over the entire facility's design life, such as 20 or 30 years, by simply multiplying the yearly corrosion rate by 20 or 30. If the result is a wall thickness loss over the facility's life of less than 6 millimeters, then ordinary carbon steel can be selected with a corrosion allowance up to 6 millimeters then. If the overall wall thickness loss is more than 6 millimeters, corrosion resistance alloy, such as stainless steel, must be selected. So, this calculation is done for each and every line of the facility, and the material is selected as I just explained. The results are shown on the material selection diagram, which uses the PFD as background and indicates for each line which is the material of construction that is selected. A more comprehensive report is issued by the Material Selection and Corrosion discipline, which is called the Material Selection and Corrosion Control Report. This document has two parts. The first part lists all the corrosion phenomenon, because there can be several different types of units, such as in a refinery or even an upstream facility, with different types of corrosion phenomenon. We have seen the most likely one, the most common one in upstream facilities, which is corrosion due to acid water due to the presence of CO2, but there are numerous other corrosion phenomena. So the first part of the document lists all these corrosion phenomena. And then the second part of the document looks at each and every process unit and what are the process conditions and what is the selected material of construction for each stream and each equipment. And the results are shown in the material selection summary, which is an attachment to the report, which shows the material selected for each service, for the different lines of the unit and the different equipment. This is the attachment of the document that shows the material selection for equipment, such as heat exchangers, pressure vessels, rotating equipment. For rotating equipment, the materials of quite a few internal parts of the equipment, such as these pumps, must be defined. This is done by making reference to categories of materials which are defined in the rotating equipment code, in the API, for example, in the API 610 for centrifugal pumps. For example, here, this pump is specified as having internal materials of construction corresponding to category D1, this one A8, and so on. Besides the wall thickness thinning phenomenon that we discussed, another type of corrosion is very common in oil and gas facilities. It is called cracking corrosion. The most common one is the one induced by hydrogen sulfide. Hydrogen sulfide, in presence of liquid water, creates what is called sour service. in sour service, there is a risk of cracking of carbon steel. Special type of carbon steel must be specified, which has low hardness and low carbon content, and also special type of manufacturing, in fact, heat treatment of welds to reduce their hardness as well, is specified to prevent this hydrogen-induced cracking. In fact, corrosion cracking induced by H2S is the most common corrosion cracking phenomenon, but there are other cracking phenomenon, and reference must be made to API 581, which lists all these types of corrosion cracking. The selection of materials of construction does not end the work of the materials specialist. He also specifies the type of coating which must be applied to protect against external corrosion. It does so by defining various systems for various types of conditions, in particular the temperature of the lines and equipment. It issues a painting specification specifying the surface preparation as well as the paint system for every service. This completes this presentation of the materials and corrosion discipline. Thank you for your attention. Goodbye.